Doped semiconductor. The resistivity of a semiconductor can be modified by adding different amounts of impurities. A rod of semiconducting material of length capital L and cross-sectional area capital A lies along the x-axis between x equals 0 and x equals capital L. The material obeys Ohm's law and its resistivity varies along the rod according to rho of x equals rho 0 exponential minus x over capital L. The end of the rod at x equals to 0 is at a potential V0 greater than the end at x equals capital L. Part A, find the total resistance of the rod and the current in the rod. So here is our semiconductor. The resistivity varies as a function of x. There is the cross-sectional area A, and we have a potential difference. X equals to 0 is at a higher potential with respect to x equals to L. The resistance of this rod is basically the integral of dr, where we consider the resistance of the portion at at an x value, a specific x value. So this is going to be the integral from 0 to L, where the resistance of this portion will be equal to its resistivity, rho of x, its length, which is dx, divided by its cross-sectional area, A. So this has a length dx here. So this has an infinitesimal thickness for this portion. Okay, so we can now calculate this integral by substituting the variation of resistivity with respect to variations in x. So integral from 0 to L. Now we have the resistivity as a function of x is rho 0 exponential minus x divided by capital L. So resistivity will be multiplied with dx and divided by the cross-sectional area A. So if I perform this integral, this is going to be minus rho 0 L over A exponential minus x divided by capital L. Now you can see the derivative of the exponential is the exponential. The derivative of inside is minus 1 over L. Minus 1 over L will cancel with minus L, and we will be left with this integrand. So this is going to work. So this will be evaluated between x equals 0 and x equals L. So if I substitute the limits of the integration, this will give me minus rho 0 capital L divided by A. Now I have exponential. When I substitute for xl, it's going to be minus 1. Exponential minus 1 minus, when I substitute for x0, exponential 0 is 1. So this is what I will obtain. So with the minus sign here, if I operate the minus sign on the parentheses, I will obtain my final answer. The resistance of the rod is rho 0 capital L divided by the cross-sectional area A, 1 minus E2 minus 1. That's the total resistance. So part A was asking me the resistance of the rod and the current in the rod. Well, the rod is set to obey Ohm's law. The current is the voltage divided by the resistance, V0 over R. Therefore, I see that the current is V0 A divided by rho 0 capital L 1 minus exponential minus 1. So that will be the current in the rod. Now moving to part B, find the electric field magnitude E of x in the rod as a function of x. Now, there is a relationship between the current density and the electric field. That's the Ohm's law. The current density is the current per cross-sectional area A, and this is going to be equal to, because I have calculated the current in part A, V0 rho 0 capital L 1 minus e to minus 1, and this is equal to electric field divided by the resistivity rho of x, or conductivity multiplied by the electric field. So if I substitute for the resistivity rho 0 exponential minus x over L, I will find the electric field. This is basically what I have written here is Ohm's law. The electric field will be resistivity rho 0 exponential minus x divided by capital L multiplied with the current density, which is V0 divided by rho 0 capital L 1 minus exponential minus 1. So the rho zeros will cancel out, and I will find the electric field as a function of x. So what is the final electric field? Electric field magnitude as a function of x is V0 divided by L 1 minus exponential minus 1 exponential minus x divided by capital L. And what is the direction of this electric field? The problem asks me the magnitude as a function of x, but because this part is at a higher potential, the electric field will point in plus I hat direction from high potential to low potential. Electric field vector points in I hat direction, which is directed from high potential to low potential. From high potential to low potential, which is from x equals 0 to x equals L. Let's move on to part C. Find the electric potential in the rod as a function of x. Okay, so we're going to calculate the potential at point x with respect to the potential at point 0. This is minus the path integral from 0 to x E dot dl, which is E dot dx, which is dx in I hat direction. So dx is dx in I hat direction, and the electric field is in I hat direction. So the dot product will be simply E dx. So this will give me potential at point x minus potential at 0, which is what we called V0, is the electric field minus the integral, so minus V0 over L 1 minus exponential minus 1. So I'm substituting for electric field. And then I have the integral from 0 to x exponential minus x divided by capital L dx. So this will give me V0 divided by 1 minus e to minus 1. You can see this integral is going to give me minus L. So minus L will cancel out with this L. The minus sign will disappear. And I will be left with exponential minus x over L, x over capital L. And when evaluated at x equals to 0, I will obtain 1. So that is the potential at point x minus V0. Now you can calculate the potential at point x. V of x will be equal to V0 times, because I'm taking this V0 to the right hand side, so this will be this added to V0. So V0 times 1 plus, now taking this into V0 parentheses, I have exponential minus x over L minus 1 divided by 1 minus e to minus 1. So this will give me exponential minus x over capital L minus 1, 1 minus exponential minus 1. Now, if I rewrite this, so this is going to be in 1 minus e to minus 1 parentheses. So 1 plus 1 minus e to minus 1, exponential minus x over L minus 1. So the 1's will cancel if I write this with the common denominator 1 minus e to minus 1. So that will give me the final answer for potential as a function of x. The potential as a function of x is V0 exponential minus x over capital L minus e to minus 1 divided by 1 minus e to minus 1. So I have multiplied this with 1 minus e to minus 1, or rewritten, I have rewritten 1 as 1 minus e to minus 1 divided by 1 minus e to minus 1. 1's cancelled. So I was left with minus e to minus 1. So that's on top here. So this is going to be my final answer for potential as a function of x. Let's move on to part D. Graph the functions resistivity as a function of x, electric field, and potential for values of x between 0 and L. Now, in part D, I have the resistivity at x equals to 0 is rho 0, because it was rho 0 exponential minus x over L. And resistivity at x equals to L is rho 0 exponential minus L over L, which is e to minus 1. Potential at x equals to 0 is V0. Potential at x equals to L is 0. On the other hand, the electric field at x equals to 0 is, if I substitute here x equals to 0, I will obtain exponential minus 1. So this is going to be x equals to 0. So this is going to be 1. So this will be the answer, V0 divided by L, capital L times 1 minus exponential minus 1. And if I substitute x equals to L, then I'm going to obtain exponential minus 1 here. So this will be V0 e to minus 1 divided by L times 1 minus e to minus 1. So the resistivity decays exponentially from rho 0 to rho 0 times e to minus 1. As you can see here, it decays exponentially. At x equals to infinity, the resistivity is 0, right? So this is going to be an exponential decay. The potential varies between V0 and 0, which also has an exponential decay here. So it starts from x equals to 0, I start from V0, and x equals to L, I reach 0. So this is going to be the potential. It starts from V0 and decays exponentially to 0 at x equals L. The electric field also has an exponential decay. It starts from this value and it becomes smaller at x equals to capital L. So it starts from V0 over capital N1 minus e to minus 1, and then it becomes V0 over capital L1 minus e to minus 1 multiplied with e to minus 1. So that's also an exponential decay. So this will be the final answer for the graphs of resistivity, electric field, and potential as a function of x. So in this problem, we talked about a doped semiconductor where the resistivity varies as a function of x. We can go to position x, and for a thickness, infinitesimal thickness dx, we can calculate the resistance, which is resistivity multiplied by the length dx. So let's make this clear here. This is basically the thickness of this portion dx. Rho dx over the cross-sectional area A. When I perform this integral between x equals 0 and L, I add up the contributions from each of these disks basically. I will find the final answer for the total resistance. The resistances are adding up because they are connected in series. The same current flows through the whole semiconductor. The current is voltage divided by resistance, so I can use Ohm's law to calculate the current. And then J is equal to sigma E. That's another way of writing Ohm's law, or electric field divided by resistivity. J is the current density, current per area. From this relationship, I can find the electric field. The potential as a function of x with respect to the origin, v of x minus v0 is minus the path integral from 0 to x e dot dx. By performing this integral between 0 and x, I can find the potential as a function of x. And finally, by noting that all of these are exponential decay functions and calculating the initial and final values at the two ends of the semiconductor, I obtain these final plots.